So, hi, I'm Xiaotong,
I'm Sissy. I'm Hannah.
and today we're going to be presenting our prediction and visualization of TDC subway delays with a neural network model. So we chose a TDC dataset, and in this dataset, we wanted more data to train our model. So we gathered the public data from 2021 to 2024, and we cleaned all of those data. We first merged them into one singular dataset, and then we cleaned the data and applied exploratory analysis, plotting various graphs to uncover patterns and trends in the data. And then based on that analysis, we developed a prediction model to predict whether or not a delay was to occur at a specific subway station, depending on various factors such as the hour, time, or any other external factors. We're going to present our exploratory data analysis.
So our first one is peak delay times, and it's separated by each subway line. So we have line 1, line 2, line 4, and we can see from line 1 and line 2 that from 2 a.m. to around 4 a.m. there's like less activity, less delay, possibly because of people inactivity. And we can also see that from line 1 that there's more activity than line 2, and line 4 has the least amount of activity, which means that we can probably exclude it from our prediction model because there's not much insights to gather from it. So this is the visualization of the geographical delay hotspots in our data. So we plotted a stacked bar chart with all of the stations on the x-axis and the number of delays by severity on the y-axis. So red is severe. Actually, green is none or little to none, which is less than a minute of delay. And then yellow is moderate, which is 2 to 10 minutes of delay. And then severe is over 10 minutes. So we found that Dundas Station, Finch Station, and Young Station had the highest number of total delays, while Shepherd Young Station took the lead for the highest number of severe delays, followed by Finch, Dundas, and Queens Park. Overall, I think every station is doing quite well. They're being run quite well. So yeah, we want to watch out for the stations with the highest number of total delays for our prediction model. And then we have our frequency of delays, and it's the average delay times of each months from the year 2021 to 2024. So we're able to get a general idea of what month has the most delay times on average, which we can see that it spikes in April and it drops around February and November and stays moderately the same in the summer. This is the summary of our findings. We just find it that there's fewer delays in the early mornings for lines 1 and 2, but they spike between 5 a.m. to 6 a.m. from Monday to Saturday. And line 4 shows minimal delays, so it's likely that we'll exclude it from our prediction model. We also found that the highest delays we found at Dundas, Finch, and Young Station, and the highest severe delays found at Shepherd Young Station.
So for how we decided to do our prediction model, because there were so many variables and factors that played into how the TDC delays functioned, we decided to implement a neural network model to capture the non-linear relationships between these different factors that contribute to subway delays. So how we trained the model was we took 80% of the data as training data, and we tested it with 20% of the remaining data. So this is our prediction model, and it's an interactive web app that you can run on your browser, and it's essentially a slider. I wonder if I can show it here because that's just, well, it's on the slide, so essentially these are points in which the subway stations, we calculate the amount of delays and the average delay times, and the color represents the average delay times, and the size of the circle represents how much delays have happened there. And using this model, a person can predict by when they're traveling by the TDC, when it might have a delay, and then adjust their traveling because of that.
Ideally, our model will be integrated into the TTC app for consumers to use as a secondary source to plan their trip ahead of time. And on this end, not only will consumers spend less time waiting for a delayed subway to come, but TTC can also pinpoint which stations have the most delayed times and narrow down a solution to solve the problem, which saves them time in checking in with all 70 stations, which can be very time consuming.
Right. So a lot, like, the major limitations that we came across was the fact that our data set had so many outliers and so many varying observations that we had to cut out a lot of that data to streamline our data collection and cleaning. So that impacted the prediction accuracy a lot. And in the future, we want to make this more accurate. We would hopefully get more real-time data and incorporate all of that into optimizing our model and refine our interactive visualization tool.
Thank you.
Thank you.
Thank you.
By the way, in case we're going to use this in the video, we just want to mention that we had a team member who worked on the machine learning aspect of this project, and so we originally had the neural network, but however, we were unable to gain the access to that piece of code and those files in our GitHub repository. So we hope that you can understand that with the visualization tool, we tried our best to sample the data and show what it would look like if we had the proper prediction data. Okay. Wait,